Imagine a star so dense that a teaspoon of its material would weigh as much as a mountain. Now picture this star spinning faster than a kitchen blender and with a magnetic field strong enough to wipe out every credit card on Earth from thousands of miles away. Sounds crazy, right? Well, welcome to the world of neutron stars. You've probably heard of black holes, those cosmic monsters that gobble up everything, even light. But today, we're going to talk about something even stranger. Neutron stars might not be as famous as their black hole cousins, but trust me, they're the real oddballs of the universe. In this video, we'll dive into why neutron stars are even weirder than black holes. We'll explore their extreme nature, from their unbelievable density to their super-fast spins. By the end, you'll see why these cosmic oddities deserve just as much attention as black holes, if not more. Neutron stars are some of the strangest objects in our universe. They're what's left behind when a massive star, much bigger than our sun, runs out of fuel and explodes in a spectacular event called a supernova. But instead of just fading away, the core of the star collapses under its own gravity, squeezing all that star stuff into a tiny space. Now, when we say tiny, we mean it. Imagine taking something with 1 to 2 times the mass of our sun and cramming it into a ball about 12 miles wide. That's about the size of a city. To put this in perspective, our sun is about 865,000 miles wide, so a neutron star is like squishing the sun down to the size of a neighborhood. The comparison gets even wilder when we look at the mass. A neutron star typically has about 1.4 times the mass of our sun, but packed into that tiny space. This makes neutron stars incredibly dense. How dense? Well, if you could somehow scoop up a teaspoon of neutron star material and bring it to Earth, it would weigh about 1 trillion kilograms. That's about as heavy as a mountain. This extreme density leads to some pretty weird stuff. The gravity of a neutron star is so strong that if you dropped a marshmallow onto its surface, it would hit with the force of 1,000 hydrogen bombs. Don't worry though, you're not likely to find any marshmallows floating around neutron stars in space. Understanding neutron stars helps scientists learn about what happens to matter under extreme conditions that we can't recreate on Earth. Now, let's talk about just how packed these neutron stars really are. Remember how we said a teaspoon of neutron star stuff would weigh as much as a mountain? Well, let's put that into perspective. Imagine you could somehow shrink the entire Empire State Building down to the size of a sugar cube. That sugar cube would still be about 1 billion times less dense than a neutron star. It's hard to wrap our heads around just how squished together everything is inside these cosmic oddballs. Here's another way to think about it. If we could pack all of humanity, that's about 8 billion people, into a space the size of a sugar cube, we'd still be nowhere near as dense as a neutron star. To match a neutron star's density, we'd need to squeeze all the humans on Earth into a space smaller than a raindrop. Now you might be thinking, wait a minute, aren't black holes supposed to be the densest things out there? Well, here's where things get interesting. While black holes are incredibly dense, neutron stars beat them in the density game, at least in terms of what we can observe. You see, black holes are so extreme that all their mass is squeezed into a single point, called a singularity. We can't see or measure this point. What we can measure is the density inside what's called the event horizon, the point of no return for anything falling into a black hole. Believe it or not, the average density inside a black hole's event horizon can be less than that of a neutron star. This is because as black holes get bigger, their event horizons grow faster than their mass increases. So, a supermassive black hole, millions of times heavier than our sun, can have an average density less than water. Meanwhile, neutron stars stay incredibly dense no matter their size. Pause. The truly bizarre properties of neutron stars make them even weirder than black holes. Neutron stars are the speed demons of the cosmos. Some of them, called pulsars, spin incredibly fast. We're talking hundreds of times per second. Imagine something as heavy as our sun but packed into a ball the size of a city spinning faster than your kitchen blender. That's a pulsar for you. The fastest pulsar we know about spins 716 times every second. That's so fast that if it spun any faster, it might tear itself apart. Now compare this to the fastest spinning black hole we've found. The current record holder spins about 1,150 times per second. While that's faster than our speediest pulsar, remember that black holes are usually much bigger than neutron stars. So, for its size, a rapidly spinning neutron star is truly impressive. Neutron stars don't just spin fast, they also have powerful magnetic fields. The strongest ones are called magnetars. Their magnetic fields are so powerful it's hard to imagine. They're about 1 trillion times stronger than Earth's magnetic field. To give you an idea of how strong that is, if a magnetar was as far from Earth as the moon, it could wipe out all the data on every credit card on our planet. It could even mess up your atoms. On the other hand, black holes don't have their own magnetic fields. Any magnetic field around a black hole comes from the stuff falling into it, not the black hole itself. The insides of neutron stars are like nothing else in the universe. The intense pressure squeezes atoms so tightly that electrons get forced into the nuclei, combining with protons to form neutrons. This creates a kind of matter called neutronium, which is incredibly dense. Some scientists think that deep inside neutron stars, things get even weirder. The pressure might be so extreme that it breaks neutrons apart into their building blocks, quarks. This would create a state of matter called quark matter, which we can't create on Earth. Black holes, in contrast, are simpler on the inside. Once something crosses the event horizon, we don't know what happens to it. Some scientists think everything just gets crushed into a single point called a singularity. Believe it or not, neutron stars have surfaces we can talk about. They have a thin crust made of iron nuclei arranged in a crystal lattice. This crust isn't smooth. Neutron stars can have mountains. But don't picture Mount Everest. The gravity is so strong that the biggest mountains are probably only a few centimeters high. Black holes, on the other hand, don't really have a surface as we understand it. There's no solid or liquid part we could stand on. Instead, they have an event horizon, a boundary where gravity becomes so strong that nothing, not even light, can escape. Neutron stars are not just dense and fast spinning. They also experience dramatic events called starquakes. These are like earthquakes but occur on the surface of neutron stars. The intense gravitational and magnetic forces can cause the crust to crack and shift, releasing a tremendous amount of energy. This energy release can sometimes be detected as bursts of X-rays or gamma rays. Speaking of gamma rays, neutron stars are also linked to some of the most powerful explosions in the universe. Gamma ray burst, or GRBs. There are two main types of GRBs, short and long. Short GRBs, which last less than 2 seconds, are often caused by the collision of two neutron stars, or a neutron star and a black hole. These collisions result in a brief, but incredibly intense burst of gamma rays, followed by a kilonova, a bright explosion caused by the radioactive decay of heavy elements formed during the merger. When neutron stars collide, they don't just produce light, they also create ripples in the fabric of space-time known as gravitational waves. These waves were first predicted by Albert Einstein and were directly detected for the first time in 2015. The merger of two neutron stars is a particularly strong source of gravitational waves because of the immense masses and extreme conditions involved. In 2017, scientists observed a neutron star merger that produced both gravitational waves and a gamma ray burst. This event, known as GW170817, provided a wealth of information because it was the first time both types of signals were detected from the same event. The gravitational waves arrived at Earth just 1.7 seconds before the gamma rays, confirming that both travel at the speed of light and giving scientists a new way to study these cosmic collisions. In conclusion, we've seen how neutron stars are truly some of the strangest objects in the cosmos. From their incredible density and rapid rotation, to their powerful magnetic fields and exotic internal composition, neutron stars push the boundaries of what we thought was possible. They're faster than blenders, denser than anything we can imagine, and home to some of the most extreme conditions in the universe. Studying these bizarre stellar remnants isn't just about satisfying our curiosity. It's about understanding the fundamental laws that govern our universe. So, the next time you look up at the night sky, remember that among those twinkling stars are some truly extraordinary objects waiting to be discovered. If you're intrigued by what you've learned today, I encourage you to dive deeper into the world of neutron stars. Check out some of the amazing images captured by space telescopes, or explore videos about gravitational waves from neutron star mergers. Who knows? You might just find yourself falling into a neutron star-sized rabbit hole of fascinating cosmic discoveries.